Hello and welcome to another thrilling and chilling installment of the Pre-Calculus Notes. This is section Unit 5, and this is about polynomial functions. And what we want to do in section 1 today is factor polynomials completely. Now, you've learned how to factor, but we have some identities and things that we want to make sure that we know how to do. The first of which is difference of squares. Okay, so a squared minus b squared is equal to a plus b times a minus b. Perfect square trinomials we need to be able to identify, and same with the sum and difference of cubes. Now, when we're talking about this, I think of the acronym SOAP. Okay, and SOAP stands for the same, opposite, and then always positive. Okay, and so when I do this, I think of the sign. So if I have a cubed plus b cubed, that can be factored into a plus b times a squared minus a times b plus b squared. So when you think about it, here's the sign. This is the same, this is opposite, and this is always positive. Same thing over here. If you have a cubed minus b cubed, then you get a minus b times the quantity a squared plus ab plus b squared. So again, same, opposite, always positive. So we'll kind of look at those and make sure that we know how to get those. The other thing we want to be able to do is identify the greatest common factor. Okay, and so we want to look at the greatest common factor of the coefficients, and then we want to look at the lowest power of each variable common to all terms. So the greatest common factor of the coefficients. So a number that we could factor out of this would be a 6. And then the variable with the lowest common, with the lowest power would be m squared, okay, out of that. Now, if you take a look at something like this, notice how all of these contain an x and a y. So the greatest common factor of 6, 12, and 3 goes into all of these numbers, so we can factor out a 3. And then we also, this has an x squared. And a y, this has an x and a y squared, and this simply just has an x and a y. Since x and y are the lowest common ones, then we can factor out a 3x and y. Okay, same thing over here. This is a b to the 5th and 2b to the 4th plus 3b cubed plus b squared. Okay, this has a 1 as its coefficient, so I can't really factor out any numbers here, but I can factor out a b squared. That's the only one that I can factor out of there, so that would be the greatest common factor there. Okay, the other thing we need to look at is factor by grouping, okay? And this is where you group things together so that you know where you can, what kinds of things you can factor out. Now, the one thing I'm going to do is you can rewrite this, okay? That's a common thing that I'm going to do is I'm going to rewrite things and basically just reorder them, okay? So what I want to do is I'm going to rewrite this, and I'm going to say 32xy plus 24x plus 4y plus 3. Okay, and the reason that I did that is because I looked at these two terms, and I felt like they had something common. And then I'm going to look at these two terms because, when I looked at the 4y and the 3, I kind of saw something here. So what I'm going to do is this. Okay, from this thing here, I can factor out a common 8. Okay, so I can factor out an 8, and I can also factor out an x. It has a common x. So if I factor out an 8x, then we're left with 4y plus 3. Okay, and you can always check by remultiplying your 8x back in, okay? And then, I can't factor anything out of the 4y plus 3, so I'm just going to leave the plus 4y plus 3, okay? But the thing that I need to notice is that I have a common 4y plus 3 in that polynomial, okay? And so what I can actually factor out is the 4y plus 3, okay? And as a result, you're left with 8x, and then there's a 1 here. You're multiplying that by 1, and it goes out like that. Okay, so you can really just think about this as distributing the 8x into each of these, and then also distributing the 1 into each of these, and you'd wind up in the same area. Okay, let's take a look at this one over here. This one I don't need to necessarily reorder. Let's just take a look at this one. I'm going to group it as r over here, and then this guy. And so what I'm going to do is I'm going to factor out an r cubed and that leaves me with an r plus 3. And then if I subtract out I can't really factor anything out of this, a minus 2r plus 5. So, I mean, I could keep going with this, but the reality is that this does not factor. And there are things that don't factor, and that's okay. Not everything is going to factor, but we have to be able to identify, try different methods and kind of look at it and make the determination that something does factor or does not factor, okay? All right, so let's look at factoring trinomials. This is really important that we are able to do this. And it was really easy to factor something when you had a leading coefficient of 1, but I want to just jump right in and do something where the leading coefficient is not 1. And what we're going to do, I'm going to show you two different methods. I'm going to show you the box method, okay, the box method, and then I'm going to show you the X method. Okay. Now in the box method, what I want to do is I want to sit down and put my first term, which is 2x squared, in this top box here, and then I'm going to put the last term 6 in this box down here. Now I have to sit there and say, okay, what two things multiply to 2x squared? So one of them is going to be 2x, the other is going to be just an x, okay? And so what I want to do then is ask the question, okay, what two numbers multiply to give me positive 6, okay? And so what I want to do is this. I'm going to put a plus 2 over here, and I'm going to put a plus 3 over here. And the reason is because if I do the 2 times 2x, that's going to give me a 4x, okay? And then if I do 3 times x, that's going to give me a 3x. So when I take those numbers and I add them together, 3x and 4x gives me 7x, okay? And that's the verification that we need to do. So what I would then do is say, okay, well if I take 2x squared plus 7x plus 6, I could factor that and say that that's equivalent to saying x plus 2 times 2x plus 3, okay? And, if I wanted to verify that this is correct, then I would just distribute and FOIL this out and multiply everything out so that we get that, okay? All right, let's take a look at the X method, and I'm going to rewrite this down. I'm going to say 2x squared plus 7x plus, what was that, 6, okay? And I'm going to identify this. We have that standard form equation where you have ax squared plus bx plus c. Okay, and I'm going to do the X method where I make an x here, and I'm going to take my a term times my c term, and then put my b term down here. So if I take my a term and my c term, a is 2, c is 6. So if I take 2 times 6, it's going to give me 12. Okay. Let's take my middle term, that's going to give me 7. So what I want to do is I want to find two numbers that multiply to 12, but then also add to 7, okay? And so what I would do there is I would say, well, those numbers are 3 and 4. So 3 and 4. So what I want to do is I want to split up my 7x, okay? And I'm going to do this. I'm going to rewrite this, and I'm going to say 2x squared plus, and instead of writing 7x, I'm going to write 3x. Actually, I'm going to do 4x plus 3x and then plus 6, okay? The reason I did that is because I want to split this up because now I can now factor this by grouping, okay? So now I can look at this quantity here and I can factor out a 2x. If I factor out a 2x, I'm just left with an x plus 2, okay? And then here, I can factor out a 3. If I factor out a 3, I'm left with just an x plus 2. So then again, I have a common x plus 2, and that's what I'm looking for. I can now factor out that x plus 2, and then I'm left with 2x plus 3. And that's it, okay? And I get the same thing. So it doesn't really matter which way you do it, but man, guys, I want you to be able to factor. That's the bottom line. All right, so we want to be able to factor something completely. And you know what, guys? This is just going to get trickier and trickier and trickier. But there's some tricks and tools to this trade and some things that you got to be able to identify, as far as something that can and cannot be factored. So the first thing that I would look at is something that we call a prime polynomial. And that's a polynomial that cannot be written as a product of two polynomials. So a prime polynomial is something that cannot be factored. Okay, so a prime polynomial, I'm going to also say that cannot be factored. And we also kind of identified this this is the same problem that we had before, okay? If you look at this, you probably want to do a grouping approach, but if that doesn't work, then we can't, we can't factor it, typically. So it cannot be factored. So what I want to do is take a look at some of these problems, okay? And so what we say here is a polynomial with integer coefficients is factored completely when it is expressed as a product of factors such that all factors other than monomial factors are prime, okay? So it's just, factored completely when you can't factor anything else out. Now, one of the tricks here, and I know that I have this all kind of written out here, but I want to look at this polynomial here, all right? Now, on the last page, we had the box method or the x method in order to do, to factor something like this when the coefficient is not equal to 1. But what I want to look at is the first thing that you'd want to say here is go, okay, well, what if is there anything that I can just factor out of this automatically? That's the first question. So the first question I always ask, is, can anything be factored right off the bat? So can anything be factored automatically? Okay. And it's really nice when that happens. Okay, so if you look at something like this, where you have 3x squared plus 9x minus 12, you can factor out a 3 out of each of those terms. Okay, look for the greatest common factor and see if there's anything that you can factor out. So if you factor out a 3, then you're left with x squared plus 3x and then minus 4, okay? So now what I'd want to do is I'd want to just simply look at that expression itself and say, okay, can I factor what's left over? Can I do anything else? Can I still factor this? And so when you have this, when the coefficient is 1, it's really nice and neat because then you can say, all right, well, what two numbers add to positive 3 but multiply to negative 4? Okay, and that would be, let me keep my 3 out here, but that would be an x, what is that? X plus 4, and then an x minus 1, okay? And this is the same thing as what we started with. Okay, but this is factored completely, all right? Because I can't factor anything else out. Now, if you ended up doing the box method or the x method on this, you would find that the individual binomials that you got could still be factored, and you'd be able to factor out a 3 out of those, okay? So, factoring completely means that you have factored everything. Okay, now, completely factor something like this. X to the 4th minus 16. Now, what I notice about this is that this isn't one of those identities, okay? And I need to remember the difference of squares, which is a squared minus b squared, which is the same thing as saying a plus b times a minus b, all right? So what I need to do here is rewrite this, because it doesn't look nice and neat. But the trick is to rewrite. I can't express that enough. I can't tell you how important it is to be able to rewrite something to see the pattern, okay? Because what I see is I see x to the 4th, okay, which can be rewritten, and I'm going to rewrite that as x squared quantity squared. And the reason why I did that is because if I, split this up, if I split x squared up into the, two different exponents, if I have an exponent raised to another exponent, I multiply them back and I get x to the 4th. But the question is can I write 16 as something squared? Okay, and so let's do that. Let's rewrite that as minus 4 quantity squared. So if you rewrite something, you should be able to go back to the original, okay? 4 squared is going to give me 16. If I take x squared and I square that, 2 times 2 is going to give me 4, so I get x to the 4th. Now what you have to identify is that I have something squared minus something squared, just like I do in my identity. So this is really my a, and this is really my b. So then as a result, I can rewrite this then as x squared minus 4 and then x squared plus 4, okay? Now, unbeknownst to us, we can still factor this, okay? What I see here is that this is another difference of squares, okay? If I rewrite this, and I'm going to do this, I'm going to say that this is just an x squared, because I have an x squared, and 4 is also a perfect square. I'm going to rewrite that as minus 2 quantity squared, okay? And then x squared plus 4, that can't be factored. That's done, okay? But now I can factor this down into x minus 2 times x plus 2, and then times what I have left, which is just an x squared plus 4, okay? And this has been factored completely, okay? Kind of tricky, but it's a lot of recognition. And I've done this problem before. I've seen this problem before in calculus and other classes. So it's something that will pop up time and time again, okay? Now let's go back over here, okay? And let's take a look at something over here. Now I want to completely factor 4x to the 4th minus 16, okay? Now the first step has been shown, and what it says is that if I take 4x to the 4th minus 16, then really, and here's how they got that. What they did was they wrote it like this. They said the quantity 2x squared, quantity squared, minus 4 squared, okay? And so if you take 2 and you square it, you get 4. If you take x squared and you square it, you're going to get x to the 4th. Okay, and what they did was that was their a, and this is their b. And so then they wrote it simply as 2x squared minus 4, and then times 2x squared plus 4. Okay, now here's where it gets a little weird, is because you can factor out a 2 from each of these parts here. So what I would then do is I would say 2 times 2 times x squared minus 2, and then this is x squared plus 2. Okay, and then 2 times 2 is just going to give you 4 times x squared minus 2 times x squared plus 2. Okay, and so that would be factored completely. All right, and that's what I mean, is that when you have this thing here where you have these numbers, these binomials, we're like, well, I could still factor something out. Then factor it out. Don't be afraid. Don't be afraid, Jim. Okay, so let's take a look, back to what we had. We have the greatest common factor. You have 2 terms, 3 terms, or 4 terms in your polynomial. You have difference of squares, difference of cubes. Some are difference of cubes. You have the box method or the X method. You have a perfect square trinomial, or you can factor by grouping, and then you repeat that until you are factored completely. So the last question I want to do is this one here. All right, and let me rewrite this down here as 3x to the 4th plus 9x cubed plus 6x squared. All right, and so, if I look at this, you're going, okay, can I factor anything out of here? Okay, I can factor out a 3, because I have 3, 9, and 6, and I can factor out an x squared. That's my smallest exponent for each of those terms. So if I factor out a 3x squared, then I'm left with an x squared plus a 6x, and then plus a 3. Okay, so now the question is can I factor this out? Can I factor x squared plus 6x plus 3? So the question is, are there 2 numbers that multiply to 3, but then add to 6? Okay, and that answer is no. I mean, you have either 3 and 1, and those 2 numbers are going to add to 4, which is not 6. So this is just factored completely. Okay, it would be cool and really awesome if you could continue to factor that, but you can't. Okay, so I know that this is a lot of information, and a lot of these problems might be hard. You might have some issues with some or difference of squares, or difference of squares, or some or difference of cubes, but deal with it and just do the work. All right, see ya. Bye.